right, so we're going to first start off with, in chapter 3, we're balancing those equations. All right. So, according to the law of conservation of mass, the same quantity and type of elements that you start with are the quantity and type that you need to end with. So, I'm going to just put up a couple of chemical equations. So, we know that you start with the reactants and you end with the products. Okay. So when you're getting ready to balance the chemical equations, I'm sorry, should I write this down? All right, so when you're balancing the chemical equations, you want to make sure that your reactants, which are on this side, you have the same quantity and type as your products on the other side. In order to do that, we use coefficients because you cannot change the formula of the chemical formula. Like you can't just change this to a 6 to make it be 6 oxygens on both sides. One thing that I like to tell my students to do is to identify and treat polyatomic ions as one thing, as one piece. So that way it makes it easier for you to balance those, especially when you have multiple polyatomic ions. So I'm going to treat this nitrate ion as one individual thing and not as being nitrogen and oxygen separate. And so you can make your list until you figure out, once this becomes more natural. So that means on my reactant side, I have cadmium, silver, and nitrate. I'm going to treat that as one piece. Over here, I'm going to put it in the same order. And then I'm going to identify how many of each of those things I have. So over here, there's one, and there's one. And over here, there's one, but then there's 2. So I have 2 nitrate ions on that side. So in order to make this even, that means I need to make 2 on this side. So in order to do that, I put a 2, coefficient of 2, in front of the silver nitrate. So then that gives me my 2 nitrates. But that also changes the silver because the silver is bonded to the nitrate. So now I have 2 silvers on this side, but only 1 silver on this side. But by adding a coefficient of 2 in front of that, then that's going to give me my 2 silvers on the other side as well. So when I look back at my equation, I have 1 each of the cadmium, 2 silvers, 2 nitrates, 2 silvers, and this number 2 here indicates that there's 2 of these. So that means there's 2 nitrates on that side. So that's one way of doing it. Now you can separate the nitrogen from the oxygen, but as a rule of thumb, I try to keep the polyatomic ions together to make balancing quicker and to make sure I don't start losing things when I have elements that are split between different compounds. Let's see. Let's do a different one. Let's do lead 2 nitrate. Reacting with sodium bromide. And then if you notice now, I'm also going to tie in a little bit of the identifying the types of reactions we have here. So I have a compound that's made up of 2 different things. I have lead 2 and I have nitrate. Here I have sodium and I have bromine. So this is a compound and this is a compound. And so this is going to be a double replacement or a double displacement reaction where you can switch either your anions or your cations. It doesn't matter as long as you don't switch an anion for a cation. So first name can switch with first name or last name can switch with last name. I'm going to choose to just go ahead and rearrange the cations because cations are written first. And so what I'm going to end up with is my lead 2 bromide. And I'm going to end up with sodium. My periodic table's over here, sorry. Sodium nitrate. And why did I do that? All right, so now I'm going to have to, now I need to balance this equation. Again, I have lead. I'm going to treat my polyatomic ion as one thing. I have sodium and I have bromine. So there's one lead, there's two nitrates, one sodium, and one bromine on this side. If I come over here, I have one lead, one nitrate, one sodium, and two bromines. So there's two imbalances here, okay? So I always start with polyatomic ions. You don't have to, it's just a preference of mine. So since there's two nitrates here and one here, I'm gonna place a 2 in front of my sodium nitrate on this side, and that'll give me my two nitrates, but it also gave me two sodiums. I continue. So since my sodiums changed from 1 to 2, I'm gonna check over here, this sodium, there's only 1. So I need to put a 2 here to make sure that I have my two sodiums. So my two sodiums here will also give me two bromines, right? Because it applies to both things. So now I have two bromines on this side. I'm gonna continue and check over here. Bam, I already have two bromines. So now when I look back, there's one lead on each side, two nitrates on each side, two sodiums on each side, and two bromines on each side. So that means I'm done, okay? So once you have the same quantity and type of elements on both sides of the equation, it is considered balanced. Let me do one with water, because that tends to throw kids off sometimes. Let's do, let me see. Sodium hydroxide reacting with, what's one of my favorite ones to do? Calcium phosphate. Okay. Yeah, we'll do this one. All right, so again, compound. So we can predict a double displacement reaction where these are going to actually change places with each other, or they're going to replace each other. So I can do sodium phosphate, Na3, PO4, sodium's in group 1, yep, plus, wrote so big, I'm sorry. Shrink that down some, okay, move over. All right, plus, where was it? Oh, calcium hydroxide. So we have sodium hydroxide plus calcium phosphate yields sodium phosphate plus calcium hydroxide. Okay. Now, again, double displacement reaction. I switched my cations because we know that sodium is +1, hydroxide is -1. So when you swap and drop, you get NaOH. Calcium is +2, phosphate, PO4, 3 negative, swap and drop here. And then again, the quantities over here don't dictate the quantities over here. So sodium +1, phosphate, PO4, 3 negative. So it was a swap and drop. Same thing here with calcium, 2 plus, hydroxide, -1. So the swap and drop. So just because there's two phosphates over here doesn't mean there's going to be two phosphates over there when you write the chemical formulas. Now, again, I notice how there's oxygen in the hydroxide and in the phosphate. This is why I treat the polyatomic ions as one piece, because otherwise I can go crazy trying to balance these oxygens. So I'm going to have sodium hydroxide, the phosphate, and the calcium. Okay, so again, sodium hydroxide, my phosphate, and my calcium. I'm going to treat them each as individual things. So there's one sodium, there's one hydroxide, there's two phosphates, and three calciums on this side. If I come over here, there's three sodiums, two hydroxides, one phosphate, and one calcium. I am going to choose to start with a polyatomic ion. Doesn't matter which one. Since I wrote hydroxide first, I'll start with that one first. There's one on this side, but two on that side. So to solve that problem, I put a 2 in front of the sodium hydroxide. By doing that, though, that also gives me 2 sodiums. I'm going to follow my changes. So 2 sodiums over here. I come over here. There's 3. So if there's a 2 and a 3, then I can't really balance that way, but I need to find the common denominator between the 2. And so let's see. Multiply that times 2. That's going to give me 6. Come back over here. Multiply that times 3. That's going to give me 6. And then I have to change this because now I have 6 hydroxides. All right, now I'm coming over here. 2 hydroxides. I put a 3 in front of it, which is going to give me 6 hydroxides. Also gave me 3 calciums. I come back, boom, 3 calciums. The 2 I forgot to write here in front of this. All right. And now 2 phosphate groups, and boom, 2 phosphate groups. Okay. So pick a spot to start with, and then you just go back and forth between the 2. But treat your polyatomic ions as one thing whenever possible. Treat it as one thing. So that way you don't try to balance the oxygens from here and the oxygens from there, because sometimes you have oxygen in more than one spot when dealing with polyatomic ions and these different types of chemical reactions. I think there's one more type I want to look at here. Let's see. Let's do phosphoric acid or sulfuric acid. Let's do sulfuric acid. H2SO4 plus calcium hydroxide. CaOH2. Okay. Now, in this case, I have an acid and a base. This is an acid-base neutralization. Anytime I have an acid, and we know that acids, the first element is hydrogen in an acid, okay? When I have an acid and a base, hydroxide, one of my products is going to be water. So this is going to give me water plus, so because this hydrogen and this hydroxide are going to come together to form water, because what's 2 H's and an O? Water. Now, so that means the calcium is now going to be with the sulfate. Sulfate is SO4 2 negative, calcium is Ca2 plus. So that means they're going to just be CaSO4 because the charges balance out. So I have sulfuric acid plus calcium hydroxide yields dihydrogen monoxide or water plus calcium sulfate. Now, think of water this way, but don't write it this way when you're doing your chemical reactions. How did water how was water formed here? It was hydrogen and hydroxide. So again, when I'm balancing, I want to keep my polyatomic ions separate. So when I go to balance this one, I'm going to put hydrogen, sulfate, calcium, and hydroxide. I'm going to do the same thing over here. Hydrogen, sulfate, calcium, and hydroxide. And then I'm going to count how many of each one I have. Where there's 2 hydrogens, there's 1 sulfate, there's 1 calcium, and there's 2 hydroxides in my reactants. Over here, remember I'm treating water as hydrogen and hydroxide. There's 1 hydrogen and 1 hydroxide because it's HOH, okay? there's one sulfate and one calcium. Now I'm going to balance. 2 hydrogens here, 1 hydrogen there. So in order to make that 2, I'm going to put a 2 in front of the water. Now, in my side notes, that gives me 2 hydrogens and 2 hydroxides. So I'm going to check my hydroxides next, and over here I have 2. Okay? Sulfates, 1 and 1, calcium, 1 and 1. So now I'm good. So if you try to balance it with just the hydrogen separate from the oxygens, again, that can get kind of messy because, let's look at this. We have oxygen here and oxygen here, hydrogen here and hydrogen here. So with it being in those multiple places, it makes it messy to try to balance it. But if you keep those polyatomic ions together and treat them as one puzzle piece instead of 2 separate elements, it usually helps with balancing things like that. Let's do one more balancing, then I'm gonna stop this video. All right, so the next one, we're going to take copper plus sulfur. And this is a synthesis reaction. And so when we take copper 2 and sulfur, we're gonna have this. Now, you know, your diatomic molecules, you have to remember those. And you also have to remember sulfur. I call it Brocliffen, this is a side note. And so Brocliffen, there's 7 of them, right? Bromine, oxygen, hydrogen, chlorine, iodine, fluorine, and nitrogen are all diatomic. So when they're by themselves, then they come in pairs. And then the 8th one is sulfur, and sulfur is S8. So that's the reason why I put them in that order, Brocliffens. So the first 7 are diatomic, and then the 8th thing is S8, which is sulfur. So you have to remember to write sulfur as S8, not just S, whenever you're doing a chemical reaction. So anyway, again, I have copper plus sulfur yields copper 2 sulfide. So I have 1 copper, 2 coppers, 8 sulfurs, 1 sulfur. So the first thing I want to do, since these are together, I want to put the 8, I want to choose the larger number and put that 8 in front of that copper 2 sulfide so that I have my 8 sulfurs there. But that's going to give me 16 coppers, and so I'm going to put 16 here. And so now I'm done. So when you have a synthesis or a combination reaction, you want to make sure that you account for the larger difference first, because it's going to change both things. Because by putting this 8 in front of this copper, this 8 is multiplied by 2, which gives me 16. It's multiplied by this understood 1, which gives me 8. Okay? So we want to make sure that in a synthesis reaction we're doing that. All right, hopefully that helps with balancing equations.